Here we go with a basic introduction to the adding and subtracting of vectors. So we're not going to go into a long-winded introduction to what vectors are. Vectors are quantities in physics that are represented as having a magnitude, a size, and a direction. And some of you might remember this guy from Despicable Me. He's called Vector, and he introduces himself to Gru here and explains that he is committing crime with both magnitude and direction. So vectors have both magnitude, a size, and a direction, and we often represent them with arrows in physics. One of the most important things in physics is recognizing when a set of forces or any kind of vector are in what we call equilibrium, and that's where the net effect of all of the forces is zero. For forces, we would say there is a resultant force of zero on an object that's in equilibrium. But it could also be some kind of momentum problem where the total momentum of something has to be zero. And you could also write that as the sum of all momentum values equal to nothing. And what we're going to see is that in order to find if something is in equilibrium, we need to be able to add all of the vectors on it together. In this case, a particle P here with a set of forces on it, we might want to add all those forces. And there's a mechanism for adding vector forces and any vectors, even momentum values. Anything that can be represented with an arrow with a size like this can be added together, and we'll show you how to do that. In order to be able to add vectors, we need to understand some very basic things. So I'm going to assume that you already know that this vector has a negative opposite vector, and it's going to look like that. So if this one is A, this one is its opposite. So it's the negative of A. So a negative vector has the exact same magnitude and acts along the same line, but its direction is reversed. So if this one here is B, then if I just make a copy of that and angle it to reverse its direction so that it has the same size but a reversed direction, then that must be minus B. And we use these, you'll see later, in cases where someone wants us to do any kind of subtraction. But we're assuming that you know this already and that you've had some experience of it. Let's say we had two vectors in a problem and we wanted to know what their total effect was. Now this could be two momentum values that had to be added, where you were trying to find like the total momentum before a collision. It could be two forces acting on an object that you want to find the total force, the resultant force. It could be a velocity of a boat added to the velocity of moving water to get an overall movement vector. So there are lots of ways you could combine them, but if we stick with A and B here that we had before, and we want to find how you would add A and B, there is a very simple method, and we call it the tip-to-tail addition. So I've just made some copies of A and B here, and if I want to find out what happens when you add B to A, I take A and I put B on the tip of it like that. So we started here and ended up here, and what this diagram is saying is the effect of this vector added to this vector is a vector along here. So the effect of A added with B gives us a vector like this. That is the equivalent of doing this and this. So this is like the resultant of A and B if they were two forces. Now you might ask, does it matter about the order that you add them in? Well, you can immediately see that if we started with B first and then added A, we get the same outcome. So it doesn't matter. A plus B and B plus A have the exact same value. So adding tip to tail like this allows us to find the total effect of more than one vector. Now subtracting vectors is complicated a little bit by the fact that it's a drawing really that we're looking at here. So we recognize some things from our early work with negative numbers, and many of you will realize that adding a negative number gives you the same outcome as subtracting that number. So 4 added to minus 3 is the same as 4 minus 3. And that's where the negative vectors come in, because we subtract vectors by simply adding a negative. So if we continue with A and B, which are again just arbitrary vectors, it could be any pair, and we think about what would happen if we subtracted B from A. Now you might ask yourself, why on earth would we want to subtract vectors? Well, it comes from the fact that we need to sometimes find the difference between two vectors. Let's say we did a pool shot where a cue ball came in like this and struck some object ball and then moved off. So come in here, hit another ball, and then ended up going like this. So we might have an initial velocity here for the pool ball, or an initial momentum even for the pool ball coming in. And we might have some final velocity after the collision that went like this. Now a question might ask you to find the change of velocity so that you could work out an acceleration or something like that. And in order to find the change, we need to take the final value and subtract the initial value. So that would be an example where you needed to subtract two vectors. So let's do it that way round. So again, we make copies of these, and then we reverse the direction of the one we want to be subtracting. So let's say we're going to subtract A first. So we're going to need a negative A. So B minus A is going to be the vector B here added to the negative of vector A. So you can see we are putting B and subtracting A from it. And we get this vector that goes from the start point to the end point. And it looks like that. So that is B minus A. That vector is the equivalent to subtracting them. So B minus A is that green one. And you might think, well, can we do this another way? Well, if that's what B minus A looks like, I wonder what A minus B looks like. So let's try that. Let's put that over there and take them again and do it the other way round and have A and the negative of B. So we need a reverse value of B. We need a vector that has the same size, only has reverse direction. And then we want to draw that out as the value of A and then the negative of B added to that. And that will give us the equivalent of A minus B. So when we do that, we get them together like this. And we started over here, went along, and then went up. So we have the equivalent of going from that start point to that end point. And we get a green vector now that represents A minus B. And you can see that B minus A and A minus B are actually opposites of each other. So they point in opposite directions, and that makes sense because 4 added to minus 3 is different to 3 added to minus 4. And we would have expected that, hopefully, that these would be the opposites of each other. So although a plus b and b plus a are the same, when you subtract, you get a different outcome if the order is changed. So let's return now to our vector equilibrium problem. If the forces on this particle are in equilibrium, then we should be able to add them all together. And something special happens when you do that. So I'll just move the particle out of the way. We know that the effect of this added to the effect of this gives you a resultant. But if we also add the effect of this, then we've gone from here to here to here. And the effect of these three forces is a vector that's from there to there. And if we add in the final value, we end up back where we started. That means that our starting point and our end point represent a vector with no size. And this is what happens when something is in equilibrium. The vectors add up to form a closed shape. So your starting and end points are the same. And it doesn't matter what order we do this in. If I take this red one and add this blue one and add this yellow one, the green one closes it again. It doesn't matter at all what order we do this, or which one we start with, which one we end up with. It keeps forming a closed shape. And that happens for any set of vectors where the total is 0. And this could be useful in examples where some unknown force has been omitted from a diagram, and what you're trying to do is put in the forces that you do know and show that the unknown force will be the thing that closes this. So it can be a very useful technique to be able to add vectors in a diagram like this using the tip to tail method. And in the next video we'll have a look at some vector equilibrium problems using forces, for example, or adding some velocities or whatever, showing that we can put the vectors together and form a diagram that helps us to answer problems.